everybody. I'm not sure it will be morning and afternoon, so I don't know how to say you morning or good afternoon, but okay, thank you for seeing this video in which I will present our results on this new diagnostic test, which is called TMek. So first of all, I will try to explain a little bit, which is the concept of malaria diagnostics and in principle what we have done with this new idea of using the magnetic properties of the infected red blood cell to develop a new diagnostic test. I will show you the results of the first prototype on field validation, and finally, the recent results on single-cell detection, which are also exciting results in order to achieve a high sensitivity to the single infected red blood cell. Finally, a few words on our social mission and the conclusion of my talk. So just to move to the problem of malaria diagnostics, I think that malaria is really a very, very important burden for humanity. It's not like COVID, it's something which is there since many, many years, I'll say hundreds of years. We have some news from Romans who already mentioned this infection as really a big problem. But right now we have 3.5 billion people still at risk of malaria, and the number of deaths is not negligible at all. So in this field of malaria diagnostic, we have to have in mind, which is the life cycle of the parasites. And the parasites is, I'll say, injected by the Anopheles mosquito, which is that's causing the transmission, because a part of life cycle happens in the body of the Anopheles mosquito, but after injection there is a human cycle, which is described here. So it starts from the infection in the hypnozoites, okay, in the liver, and then there is the release in the blood of merozoites, which infect the red blood cell, and you have the erythrocytic stage. In the erythrocytes, in the red blood cell, the Plasmodium parasite proliferates, and it gives rise to different stages. You see the ring in which, okay, the aspect is that of the ring, as a matter of fact, and then you have the trophozoite and the schizoid, and then you have the rupture of the cell membrane, which gives rise to the fever attack, and then the release of new parasites, which starts to amplify the number. It's really a positive feedback, which gives rise to a very serious condition for the patient. What is interesting is that during this life cycle, the gametocytes, the parasite feeds off an hemoglobin and transforms hemoglobin into hemozoin crystals, okay, which are not critical for their life cycle. They are not really a problem like the TMek, which is the result of the digestion of the hemoglobin. And the interesting story for us is that these hemozoin crystals are magnetic, and this was the origin of the interest of myself and my group into malaria. So the available diagnostic tools are represented here. The gold standard, the honorary gold standard is optical microscopy. So you start from a blood smear on a microscope slide, and then there is a microscopist that, after staining by Gebser, is able to recognize by eye, after proper training, the presence of some infected red blood cells or some parasites, because you also destroy the cell membrane for some tests. But okay, the critical aspect of this diagnostic tool is that it takes some time, so you need at least, I'll say, 1 hour, something like that. The limit of detection can be low, but it strongly depends on the ability of the microscopy. So it's really operator dependent. And there is no quantification, because I'll say it definitely depends on the capability of the guy doing the job. In the last 10 years, we have seen the appearance of rapid diagnostic tests. That's a typical case of a lateral flow device, like that for pregnancy we are used to, or those for COVID we have been used to during last years. It's an antigen detecting rapid diagnostic test technology. So it's rapid, 15 minutes, but the limit of detection is 200 parasites per microliter, and there is a lot of false positives due to some problem in the, I'll say, gene deletion, and so not all, I'll say, species are detected in the same way. And recently, we're seeing the appearance of PCR-based tests, based not, I'll say, on the standard version of PCR requiring thermal cycle, but isothermal amplification version, which is the LAMP. Very high, I'll say, sensitivity, so the limit of detection could be, I'll say, just a few parasites per microliter. But here the problem is sample preparation and not so easy. So right now it's not a technique with a strong impact on on-field diagnostic. So coming to TMek, so the idea was to use magnetic properties, and now you see the reason why Mosaic crystals are super paramagnetic. The reason is that you have transformation of iron 2 plus into iron 3 plus ion spin states, so that you have a paramagnet. And the interesting story is that if you look now at the different species of Plasmodium, Falciparum vivax, Malaria, so they have different chemical behavior, but the magnetic behavior is almost the same in the sense that all these species produce emulsion. So in this sense, a test which is targeting now the magnetic properties of the cells is really a pan-Plasmodium test. It's not so sensitive to the species. Here you see also the stage, the ring stage, which is the initial stage, the trophozoite, the skeleton, the gametocyte. You see the evolution, which also gives rise to an evolution in the content of emulsion, which means also an evolution in the magnetic susceptibility, the volume magnetic susceptibility. Here you see that you start from healthy red blood cell with the, I'll say, negligible susceptibility with respect to water or the PBS or the plasma, which means they are essentially undistinguishable, okay? But when you start with the infection, the ring stage, you see that there is a tiny difference, 0.8, 10 to the minus 6. And then when the, say, the infection, I'll say, is moving towards, I'll say, the final stage, which is that of the skeleton, you see that you will find something which is in the order of, I'll say, okay, here 1.8, 10 to the minus 6. So the gametocyte, which is the stage of, say, the final transmission to the Anopheles, you see that you reach something in the order of 200. So it's very, very huge because the amount of emulsion is very, very huge. And for emulsion crystal, you have 410 to the minus 6. So I'll say at the very beginning, we have been studying the properties of the emulsion crystals, and we realized that, okay, they are magnetic, super paramagnetics, 4 by 10 to the minus 4 is susceptibility, and also, I'll say, what is relevant for us, they behave as insulating particle, at least in DC, but also in AC. And then we moved to our idea. The idea was to use now the competition between gravity and attraction, magnetic attraction, in order to really separate infected red blood cell from the healthy one. So you see that in principle we have two possible configurations. In the horizontal one, we have the microchip with some magnetic elements attracting the infected red blood cell, so that the magnetic force counteracts the gravity force. And the vertical configuration is not exactly the same in the sense that the magnetic force is perpendicular, so that the magnetic force affects the motion, and in any case, there is an attraction toward the microchip. And our idea, the concept is, let's try to attract towards some magnetic elements on top of which we fabricate some electrodes. Here you see now a single nickel concentrator, which is a flux concentrator, a field concentrator, producing the gradient which is needed to attract the infected red blood cell with some electrodes on top. And this is the idea that we will exploit, and we will see. It has been exploited in this microchip, which was the first prototype, which has been also pre-validated in Camerun in 2019. So this is the vertical configuration I was talking about. You see now that we have our chip with some nickel concentrator and some permanent magnets placed on the rear of the chip. So as a result of the macroscopic gradient produced by these two neodymium iron boron magnets and of the concentrator that are placed on the chips, we have the attraction, the separation of the infected red blood cell, the pink one here with respect to the red one, which will simply sediment. And this is obtained because we are able to produce very huge gradients. So from some calculation, it turns out that for a single Amazon crystal, you will need something in the order of 10 to 13 amps square over meter cube, sorry. For infected red blood cells, you need something more on the order of 10 to 14, 10 to 15 amps square over meter cube. And this is achieved here. You see some simulation, couple simulation, using two ferromagnets with the two North Pole which are facing each other. But on top of this, I'll say a microscopic gradient, we need now something which is capable to concentrate now the corpuscle onto the single concentrator. And this is achieved by means of this nickel concentrator, as you can see on this plot of the logarithm of the gradient of H squared. In any case, the values are almost those required here, which means we are in good condition. And this is what happens, okay? Due to this local field gradients, with some COMSOL simulation, you see that during the sedimentation, the infected red blood cells are attracted toward the magnet, and you see this almost linear motion here. It's a straight line here. But okay, in proximity to the chip, they feel, the cells feel the attraction of the concentrator, and they concentrate on top or on the surface of the concentrator where some electrodes are placed, which is the impact on the impedimmetric signal. So we typically apply a fixed voltage and we measure a current, which is an AC measurement carried out at 1 megahertz in order to probe the resistive part, which is that sensible to the presence of the red blood cells. And what happens when we approach the magnet, we start capturing now the cells. You see that there is a change now in the current. So it's a negative variation, which means the current is decreasing because the proximity of the red blood cell on top of the electrodes creates an additional impedance due to the fact that the resistance of the red blood cell is higher than that of the medium. So the current decreases till at 300 seconds in this case, we move the magnet, so that we remove the magnetic field, and so the particle will fall down here, they are no more captured, and the current recover its initial base. That's the basic principle, and that's how it works in practice with the first prototype we have fabricated here. So essentially, in this case, you see we have a cartridge, we load the chip here, and then the operator is loading now the liquid, which is the blood in the real case. Now you close cartridge, you insert it into the reader. This was exactly the first prototype which has been used during the first validation in Camerun, and then you see what happens for healthy patient and for malaria affected patient. There is initial, let's say, decrease, which is something due to spurious effect, but just for a malaria affected patient, you see this increase, which is that telling you that really we have been capturing something at this stage. And then when you release, when the motor is up, so you release the particle, and this jump is then proportional to your signal. And we have tested the first prototype first in Milano at Sacco hospital on negative control. Healthy donors, you see no jumps are seen here, but on a plasmodium vivax case for a patient which arrives at time 0, you see the signal here with this amplitude. After 25 hours, after the beginning of the treatment, the signal is reduced here, and after 48 hours, there is no more signal, which means that we have been able to follow the evolution of the illness during the treatment. Okay, now what about sensitivity? In order to probe sensitivity, we have been working on a synthetic sample, which means it was blood of an healthy donor, in which we have been spiking some treated red blood cell. Red blood cells are treated in order to produce transformation of hemoglobin into meta-hemoglobin, which is paramagnetic. So we are mimicking the behavior of infected red blood cell, and you see that there is almost linear behavior of the amplitude of our signal over more than 3 decades. And then when we increase the capture time here, it was 4 minutes, 5 minutes, now it's 10. We were able to reach, I'll say, a limit of detection of the order of 10 infected red blood cell per microliter, which is definitely better than that of the microscopy and better of diagnostic cell. There is also limit of detection for free hemoglobin, but in this case not so relevant because the system was designed for infected red blood cells, which are bigger. So a single crystal of hemoglobin is 600 nanometer long, while infected red blood cells, its disk whose diameter is on the order of 8 microns. But in any case, we are also able to detect free hemoglobin. So we went to Malaria, which is a small village in Camerun, and name TMek comes from the name of malaria, local language, which is TMek. And okay, now you see the phases of training of the personnel, our system installed in the laboratory, and the training of the operator, which was manipulating now the infected red blood cells from patient. And so we had a possibility to test a sample over something in the order of 100 patients, or I'll say patient with suspect of malaria. And in the end of the day, we had some invalid tests, some probably in some case, but 75 samples are really meaningful. And starting from the comparison of our test and rapid diagnostic test, having with as reference microscopy, we were able to find the figure of merit of the test, which is sensitivity, which is capability to detect I'll say, positive case, which means people affected by malaria. And in this case, it was 100% in the sense that all, I'll say, patients with malaria were really detected. And specificity is the ability to have no false positive. In this case, it's not so good. It's only 69% for our tests because we have some false positive. And here you see the comparison with rapid diagnostic tests. If you look now, they are robust, they are more or less over there. But the big difference is that in our case, statistics not as good as in case of RTD because we had just 75 cases. In their case, we have, say, many thousands of cases, probably hundreds of thousands of patients, so that this is definitely better than ours. And in case of capillary test, the situation is slightly better, at least for BA sample that we had. Capillary test means that you take just it's a prick test. You take just a drop of blood from the finger, so finger pricking, and in this case, so the number of false positive was 0. I can say the statistic is good, but it's an indication that the aging of the sample is critical because in case of the finger pricking, it was immediate, I'll say, just after the sampling of the blood, we had, I'll say, the analysis. In the other case, the sample were lasting for up to 20 hours. And in this case, some blood degradation can give rise to false positive due to hemoglobin degradation. So these are the TMek feature after validation in Camerun a few years ago. So we had the first evidence of possibility of a direct and automatic quantification and parasitemia, also of the circulating pigment. We had evidence that it could be a plasmodium test because most of the patients were affected by Plasmodium falciparum, which is the most widely diffused in Africa, but we also have some vivax case, some ovale case, and we had one vivax also here in Milano, and we have seen that just on 5-10 minutes we could achieve sensitivity, which is good enough in the sense that we had, I'll say, possible limit of detection on the order of 10,000 parasites per microliter. The storage conditions are not critical. We have no reagents. It's a physical method, this one, and the sensitivity and specificity are 100% and about 70%. Not too bad. So with our TMek white paper, with the progress, so the guys were very, very glad. And we also demonstrated that looking at the shape now of our curves, this is the current as a function of time when we approach here and we release our magnet. So we see these jumps, but the shapes is completely different, meaning that the rings and electrozyte metacytes can be distinguishable using now this technique. So the final question is really quantitative on field? It was quantitative in the Sacco laboratory, but not on the field, not too much, because you see the dispersion, our results, the function of the concentration And as you can see, there is something that could be a sort of linear behavior, but it's not so satisfactory. So it's feasible, but it must be improved. And that's why the team has been working on the new version. So I will just show now what has been done last summer in Rome and the Istituto Superiore di Sanità for a different arrangement of concentrator, electrodes. Many things have been improved, and this is the result of the in which we have also possibility to observe with the microscope what is going on during the attraction, during the capture. And let's see what happens with this video. You see that now signal, the time is flying, and here will be a first jump. First jump is due to the attraction of the first. So this jump corresponds to a single part. Now second one is arriving, you see a second jump. Now nothing is happening, but now we will see that here there will be a third jump. So a new cell has been captured here. So that's a demonstration that we can really achieve a single cell sensitivity, and this is obviously very interesting in view of the deployment of this capability towards a very, very high sensitivity. And just to show you, I'll say what can be done by analyzing also the step amplitude statistics, we were also able to distinguish the different stages. For gametocytes, which are the last stage that's giving rise to transmission, we see that looking at the distribution of the jumps amplitude, you see that there are some peaks here corresponding to 1, 2, 3 cells that can be captured at the same time. And so what is interesting is that more or less, they are centered at, here you have something in the order of 12, something like that, 15. Now we have something at 30. So you see that, for 2 cells, more or less the double, which is good because the system could be linear. But okay, for trophozoites, the histogram is slightly different, which means that the amplitude is different. So it seems that the step amplitude analysis can also be used to disentangle the corpuscle. And that's the story. This is the conclusion. So we have developed this new test, which is based on this idea of the separation, of selective separation of the infected red blood cell and the mosaic crystal by using competition between gravity and magnetic force. And it looks quite well. Right now we are moving towards, a more, extended validation with different numbers. Okay, that's the end of the story. I just anticipated the fact that we have a social mission. That's also something which is interesting because we have IP protection, but we decided, to develop a sort of social pattern, which means that all, the inventor gave up the rights, and the idea was to reinvest the revenues, possible revenues in social projects towards really the eradication of malaria. So thank you very much for your attention, and enjoy your conference.